Okay, this is the start of chapter 18. This is 18.1, Introduction to Galvanic Cells. First thing we need to do is just kind of explain what is electrochemistry. So chapter 18 is electrochemistry, so we'll define that. Then talk about how does a galvanic cell produce electricity? What is cell potential or voltage? And what parameters of the galvanic cell affect the voltage? So not all of those questions are getting answered in this PowerPoint. Some of it is getting answered in the inquiry packet that you guys are going to do in class, as well as our discussion of that packet afterwards. So this PowerPoint you're watching is basically just to get you started. Now, if you have not done the homework yet, which was the first page of that inquiry packet, remember there was some written homework on that first page, pause this video, go do the homework, and then come back, because the video is a lot easier to understand if you've already reviewed the redox reactions like I'm asking you to review. So, assuming you've done the homework, we keep going. Electrochemistry is the interconversion of electrical and chemical energy. That means turn electrical into chemical or chemical into electrical. So we can generate electricity from a chemical reaction, or we can use electricity to force an unfavorable reaction to go forward. So we talked a little bit about that in chapter 17 as well. A galvanic cell is simply a battery. It's an apparatus used to generate electricity from a thermodynamically favored redox reaction, specifically redox. It's also called a voltaic cell. Those words are used fairly interchangeably. Galvanic and voltaic mean the same thing. They're batteries. And it's named after people. So they're both Italians, Galvani and Volta. I don't know if they were working together, working separately. I have no idea. But both names get used. We're talking about redox reactions a little bit. Redox reactions involve a transfer of electrons. Remember how we had transfer of ions, transfer of protons, transfer of electrons. That's kind of how we designated the three types of reactions in quarter one. So electricity or electrical current is just a flow of electrons. So if we could catch the electrons that are being transferred in a redox reaction, then we can generate electricity. We've got a flow of electrons. Looking at this redox reaction, I want you to predict the products. Use iron 2 in your product. Make sure you put some states of matter on it. So pause for a second, fill in some products on your packet. Hopefully you came up with this. Hopefully you crisscrossed the iron and nitrate properly, and hopefully you balanced it, because this isn't balanced yet. Now it's balanced. Next, what I want you to do is write the half reactions. Now, if you need to put this into net ionic form first in order to remember how to do the half reactions, that's fine. If you can do it from here, that's fine as well. So again, you pause for a second and write in your packet, write the two half reactions down. Hopefully you came up with something like this. So check them over. Is that what you wrote down? Keep in mind that the two half reactions need to add together to go back to the net ionic. So obviously nitrate is our spectator, it's not showing up. If you add those two things together, there's 2 electrons on the right side of one reaction, 2 electrons on the left side of the other reaction. Those would cancel out. Your net ionic equation should not show electrons. The whole point of writing a half reaction is to see the electrons, to see how many electrons are being transferred during this reaction. So next, on those half reactions you just wrote down, I want you to assign oxidation numbers and then label one of the reactions as oxidized and the other as reduced. So pause again, think about it, write some stuff down. So hopefully you're seeing that the oxidation number on the iron is 0, on the Fe2 plus is 2 plus. On the Ag plus, it's 1 plus. On just Ag, just silver by itself, it's 0. So the iron will be oxidized. It's losing electrons. See, it lost them, and there they are on the right side, separate from the iron atoms. The oxidation numbers increased. We went from 0 to 2 plus. The Ag plus is reduced. It gained electrons to become Ag, just neutral Ag. So the oxidation number was reduced. It was 1 plus and now it's 0. It gained electrons. So look at there they are being added on to that silver ion. The silver ion is gaining them. So there's a spontaneous transfer or flow of electrons in this reaction. Because it is thermodynamically favorable, it is going to go forward. The iron will replace the silver, and electrons are transferred from one place to another. How many electrons are being transferred? Go back and look at those half reactions again. How many? 2. 2 electrons. That's what you're seeing in the half reaction. So 2 moles of electrons are transferred per mole of reaction. Every time you do this reaction, 2 electrons move from one place to another. So if we could harness those electrons, then we could do work. So this is how we usually do the reaction. We put a piece of iron into a silver nitrate solution and the reaction starts. The problem is with this setup, we can't harness the electrons. We can't get at them. We can't get them to then flow through a wire and go somewhere. So this method of doing the reaction isn't going to work. Instead, we're going to create a galvanic cell. So this is a schematic of the galvanic cell. We're separating the iron from the Ag plus solution, and it allows us to capture those electrons and use the electricity to do work. So what you're going to be doing in the inquiry sheet is figuring out what this cell is, how's it constructed, what are all the parts. You're going to be labeling everything. You're going to be figuring out how does all of this work. So when you get to school on Tuesday, first you're taking a test, but then you're going to start the inquiry worksheet. And you'll go through all of that to understand what's going on in this cell. So that's all I need you to do. As long as you've done the homework on the front of the inquiry packet, you're ready to go.